Hi, I'm Kris Geusebroek from the Netherlands, and I'm going to talk about how we created a large Neo4j database with the help of our Hadoop cluster. The agenda is looking like this. I'm going to tell you what we did, why we did it, especially how we did it, and a little bit at the end who did it and who I am. So I'm starting with the two technologies we used. We used Hadoop and Neo4j. Hadoop was mentioned a lot more than Neo4j this conference. I assume you all know, but I stole the Wikipedia definition to get a little picture of what the technologies were. So we use Hadoop, HDFS, and the Mapreduce frameworks. And we use Neo4j, the graph database, to create pretty pictures like the ones below. And the use case is that we wanted to create large Neo4j databases and do that multiple times. So it's not a one-time exercise where you basically import your initial data and then add a few nodes and a few edges. But we wanted to look at the data differently from time to time and recreate the complete database. The test setup we worked with was a Neo4j database with 30 million nodes and 700 million edges between them. Nodes had nine properties, and each edge 4 properties, and that all was stored in Neo4j for querying. You might want to know why we did that. We used Neo4j to create visualizations because Excel does a lousy job there with large databases. And we wanted to use that data in Neo4j for doing some agile exploration. Have a look at one person in the graph and see, it was a financial network, see where the money went from that person, how many steps were between this person A and person B. And we needed to have not one way of looking at the data, but multiple ways. And because at one time we wanted to look at it on a transaction basis, the other time on an aggregate basis. So we wanted to recreate the database a lot. So we start with the database, do some exploration, and then throw it away and use another database with different data and have some exploration there. You have multiple ways of creating a Neo4j database. You can use the Java API, the REST API. You can use Cypher, that's kind of SQL for graph databases, to create nodes and edges. You also have a batch import functionality that comes with the Neo4j database, and you have my way of doing it, and that's what I'm explaining to you now. First, the more normal ways of creating a database is just adding nodes and edges one at a time. But Neo4j being transactional, that has a lot of transaction overhead. Every node you insert, and with the 30 million nodes we wanted to do, that was a lot of overhead. So that's not a good way to do it. The batch importer, there they have left out the transactional part, so the overhead is less. So that was a good way to start. So first we started with the normal batch importer. You write some code like this, creating a node with a map of properties that you have read from the input text file, CSV, tab separated, something like that. When we created that large database, it took us about 30 hours waiting time on our desktop machines. So the first improvement we did was we had a Hadoop cluster, so we stole one of the data nodes and used that one for creating the database. That improved. It took 16 hours or so on that machine. The problem was only that you have to get it to the machine where Neo4j is running, and that took another 2 hours. But since we had a Hadoop cluster, we had a Hadoop cluster of 16 nodes, we thought, well, why don't we use that horsepower? And the other advantage of doing it with Mapreduce was that I could learn me some Mapreduce paradigms along the way. So how did we get going? I want to make clear that Neo4j doesn't have to be running. We don't need Neo4j. We are building the database from the ground up, and we're doing that by creating the underlying file structure. Neo4j has 20 or so different files, where each file has its own purpose. There are files storing the used IDs. There are files storing the nodes, separate files for the edge information, and the properties are stored in separate files. And if Neo4j has access to this file structure, it can become a running database. So we had to investigate what was the internal representation of a node and an edge in those files. We didn't have to do that all from the beginning. Kris Geusebroek, he wrote a blog post on the file structure in Neo4j 1.6. Currently 1.9 is the version to be used. But he did some work before us, explaining how the file format looked. I'm going to, I don't want you to read this blog post right now, so I'm going to repeat some of the important information from that post. And that is that a node here in the top has a 9-byte reference in the file. So it has a use flag where you can, which is used for deletion. It has a pointer to the first relationship and a pointer to the first property. And together with the relationships, where you have a pointer back to the node, another pointer to the to node, a type of the relationship, and the previous and next for both the from and the to node. That gives you essentially a doubly linked list on disk. Since pictures say more, I created this little graph. It's me being a speaker at Berlin Buzzwords. There are properties between the curly brackets, so the place, Berlin, the venue, Kulturbrouwerei, but also a property, the date at the relationship. And with this little graph, you can see a little how it works. So the red arrows are the pointers from the nodes to the first relationship, and the blue arrows are the pointers to the first property of a node. And then within those relationships, you have a pointer to the next, and the green lines are we're pointing back to the nodes again. And the black arrows, I only drew them at the property level. There you can see the doubly linked list elements pointing back to the previous and pointing forward to the next property. So this is the file format that we wanted to create. And the position in the file is important. The position in the file tells you which node you are working on. So this is a hex dump of the node property store. The colors I did add myself, so you can see the 9 bytes in the bluish color are the node number with the ID 0, and then you have 9 bytes for node number 1 and so forth. So since the position in the file is really important, we needed a kind of row number generator. The data we had a key which was a string, some account number with string data, character data in it. So you can't use that as a row number. So you had to create it yourself. Unix has a row number generated, built-in cat. If you could put the man page on, you can see the -n. It puts a number before the output lines. That helps, but we needed to distribute it cat minus n. So we could convert the parts, the input data on the left, and put the row number in front of it. We wanted to do that with our Hadoop cluster, and the easy way out is doing it with one reducer at the end, which puts in the numbering, but that's not fun, right? So we did it in a real distributed way, where we had the mappers emit the records as is, and have access to the hashing algorithm where the mapper would know to which reducer the data is going, and it could increment a counter for that reducer. At the end, when the mapper is done with the data, it could emit also those counters. I'm going to lead you through an example to make it more clear. So the mapper first initializes the counters when starting, reads the input, emits the input as is, and increments the correct counter based on the hashing code it gets from the partitioner. And at cleanup, it emits all counters that it incremented for the data it saw during the input. This is some pseudocode, but I have here a slide with pseudocode and some data. So on the left, you see again the small input with the hashes at the end, and you start by reading ABC and emit it, and increment the zeroth counter, and then DEF, and it increments the following counter. And you have a separate mapper for the data after the split, and it does the same and emits also the counters. Then you have the reducer, and the reducer processes all those counters at first to calculate the offset. So the first reducer, reducer 0, doesn't have to, it can start with 0, so it doesn't have to process those counters. And while emitting the input data, it adds the counter to it and then increments. The following reducer, reducer number 1, processes first from the two mappers it got several values, first 2 and 1. So the offset is 3, and it starts emitting at 3, and then 4, and so on. And reducer 2 gets different values, higher values. And so this way you have the distributed cat minus n. Well, is that all? Well, no. You have to do something between the mapper and reduce phase. So we have a custom partitioner. That partitioner calculates the hash to know, based on the input key, to which reducer it goes, and you have to make it available to the mapper code. And a grouping comparator to be sure that in the reducer you have only one call to the reduce method. And some custom writables to make sure that you can put those counters in front of the values. After putting it to the Mapreduce job of the row number generator, you have your original data with a row number, and then you can do the following steps to generate the real Neo4j files. And it's a bit simplistic here. In the total is it 12 Mapreduce jobs following each other. But we start with the properties, the output of the properties and the nodes and edges again. Join nodes and edges to get from the functional ID to the row number ID. And then after that, output the rest. So starting with the properties, you have to start with the properties because every node has a pointer to the first property, and they optimize the property store a lot. So one property record can hold multiple properties. So it's not that simple as saying, well, the first property is my node ID times the number of properties I have. That was the first mistake we made, but we learned. So then we started with the properties, and then you can do the optimization, and you really know what was the first property you would encounter. And another advantage of doing the properties first is that after you have created the Neo4j property files, you can leave that information out. So you only have to keep the node ID and the functional ID, and the rest of the properties you can leave out. So you end up, after that first job, with smaller intermediate data which you can work on. After that, the output of the properties, we also output the node ID with that first property ID, and with the edges for the same, and you leave out the real property information. Then you have to go from the functional ID to the real row number ID. So you have to join the node information with the edge information. If you have done that, then you can output the real node file for Neo4j, because you know which was the first relation. So you have that reference, and you already had the property reference. And you have to do some self-joining with the relationships to know which one is really the first one. But well, I simplified it for this presentation. And the last thing is that you can output the edge information with the previous and next pointers and stuff like that. After doing those Mapreduce jobs, it's just simply do Hadoop -cat on the data, the parts that are written, and concatenate them to have a working file for the Neo4j database. It's a little more times because we store the relationships in separate directories and the node files. But this is 28 lines of bash to get it from HDFS to the machine where Neo4j can be started afterwards. Okay. Just a little about myself. This was the technical part. I've wrote a little Cypher query to let you know who I am, what my email address is. I am part of the Dutch Hadoop user group meetup and the Graph database meetup. So there I can combine these two technologies also. My Twitter handle is Kris Geusebroek, and I'm on GitHub also. To end this presentation a little earlier than I was expecting, but that's no problem. I guess being the latest one in the row. Just a little list of things that we need to do to make it complete. Neo4j uses internally Lucene indexes. It would be great if we could create those Lucene indexes on a few of the properties during the Mapreduce cycles we do. We skipped the array properties. The Neo4j has all primitive properties and string and array properties. The array properties we skipped because it was work, and we can kind of basically do the same as we did with the string properties, but it's not in there yet. The guys at Neo Technology are not resting, so they created or are busy creating Neo4j 2.0, and there the file structure is changing, so we have to keep up with them. So that's another thing to do. And at the last session of the GraphDB meetup, somebody told me that it would be great if we could do it also the other way around. So we have the Neo4j file structure and create something relational or tab separated from that to do graph global analytics on the Hadoop cluster. So those are the things that well, we can work on. The code is on GitHub, so if you want to use it, please do. And if you have requests of things you want to be built in there, let me know. And time for questions, if you have any.
Okay, thank you to the speaker.
Okay, thank you very much.